and today we are joined with the wonderful Professor Jonathan Heckman from the University of Pennsylvania. Professor Heckman is an expert on string theory and has also worked extensively on cosmology uh, and various things on the interface of them both. And we cannot be eh, uh, more grateful for him to be with us today. So, uh, uh, yes, without further ado, let's get into it. Professor, um, like, were you into physics and the sciences from like uh, a very young age, or like were you into it from your high school days?
Yeah, so I was, well, first let me say thanks for having me on. It's nice to talk with you. I would say that I was interested in kind of math and also even like, literature from an early age, and became more interested in sciences, maybe about like age 8 or 9 or so. And so from about that point on, I started becoming very interested. I remember being interested in things like physics, but also, I remember early on I had a teacher who was very interested in insects and learning about insects. And so I started, that was kind of my first experience with, something more advanced in terms of science. Not so much on like, physics itself, but on just learning about the names of insects and how do I classify them and identify them. So, yeah.
Yeah. Uh, so that is incredibly fascinating. Like, I think a lot of the students these days, and at that time as well, were like quite uh, heavily influenced by Dr. Carl Sagan. Like, was he also a big motivator for you?
Sorry, can you say again?
Like, basically, were you also motivated by Dr. Carl Sagan?
Carl Sagan, to some extent, I would say that who was really, I was actually kind of motivated by seeing scientists in various movies and things like that. So I remember watching like Back to the Future and things like this and being excited, excited more by that. I remember also reading like some popular lectures and popular articles by Feynman, Richard Feynman. I thought those were very inspiring. Yeah, I would say those were kind of the major influences, like, that got me kind of, from a popularization standpoint, kind of excited about science. Yeah.
So basically, when did you thought that yes, I would become a scientist one day?
Yeah. I don't know. It was more like I wasn't sure what else I could do. so I was always very interested in it, and it became much more interesting to me in high school, and then as an undergraduate, I became, I started getting involved in research, and then at some point I started thinking I wasn't sure what the alternatives for me were. So I wasn't. So it was more like, well, if I'm not going to do this, then what am I going to do? So that was kind of what. By the time I was like finishing undergraduate, I was applying for graduate schools. And, a lot of my friends were applying for graduate school too. And some of them went straight into business or things like that. But it was basically at that point that I decided, okay, I'm going to have to try and do this because I'm not sure what the alternative is for me. So.
So that is like incredibly fascinating. So basically, what was the reaction of your parents when you told them that you want to be a scientist?
Well, my mom was pretty, sympathetic, and she was willing to support me no matter what. My father was kind of worried, and I think he still is worried about, whether I make enough money or anything like that. So, especially like early on, I was also very interested in math, and he was worried that like, well, if you're not, you should do what you're interested in, but you'd also be able to, make a living doing it. So I think that was one of his worries, and he himself is an academic, and so it's and he knows, like, therefore, like, it's kind of difficult to get a job, and so he was worried about that, I think. But they were both supportive, I think, about the general plan.
Yes, so that is quite inspiring. Yeah. Yeah. So you told that you got involved in research during your undergraduate days. So basically, how did you transform as a physics student in your undergrad, and like which professor inspired and you the most in that aspect?
Yeah. So actually, I started even in high school. I was pretty lucky because there was I went to high school near a university, and they had like openings in the lab, in an astrophysics lab. So I got to work in an astrophysics lab there. And so initially, I was kind of doing a lot of things where I was like soldering electronics and just working a lot with my hands, and also doing writing software. And I continued doing that like in my the first year between like freshman and sophomore year, and then between sophomore and junior year, I guess, I also worked in a physics lab. And it was at that point that they had a few like quantum field theory textbooks like laying around in the office, and nobody else in the lab was touching them. So I decided to take them, I decided to take them home with me, and I started reading that, and I found that actually more interesting than the stuff I was doing in the lab. I mean, plus I was also not very good, building things with my hands. So that was the other thing. So there was like this one point where we had all this like delicate glassware, and I broke one of the pieces because I pressurized a piece of glass, and so it could have been a big disaster if if I had turned one other knob. And so at that point I realized I probably should be doing something more theoretical than experimental oriented. So basically after that I then went. I started talking more to theorists at the university, and they gave me some things to think about and research projects, and so I started talking more with theoretical physicists at university, and so that was kind of basically from like junior year on. I started focusing more on the theory side because I seemed to have more talent for it, and I was more interested in it.
Yeah. Yeah. So like you told that you like wanted to go into mathematics like as a high school student and also as an undergrad. So basically, what course in mathematics like fascinated you the most in your undergraduate days?
Well, so there was one problem I kind of set for myself, which was probably too ambitious. But I wanted to prove that the Euler-Mascheroni constant was a transcendental number, and so I failed at this. And so I spent like an entire summer trying to prove it, and this was when I was working in the physics lab. And so I decided at that point, well, this didn't work out so well. But I mean, I was always very interested in kind of the not so much on the number theory sides, but more on like the geometric aspects of mathematics. So especially the idea of like curved spaces and things that don't necessarily follow the standard Euclidean axioms. So I always found that very fascinating, and so I took a bunch of classes on geometry of various kinds because I was so excited by the idea that this could have something to do with not just pure thought but also potentially our universe. So I mean, I had known from popular accounts that things like there was this notion from Einstein's theory of general relativity that differential geometry was important, and so I was excited to learn more about that and see how this abstract world of math was connecting to that. So those were kind of the areas of math that really pulled me in initially, like things connected with kind of geometry. And in some sense, I got very lucky in graduate school because my PhD advisor was like one of the main people who was kind of pushing forward the program of connecting geometry with physics. And so it was kind of almost like a perfect fit in terms of things I was interested in and things that he was known for kind of developing. So that was kind of lucky on that side too. Yeah.
Yeah. So like yeah. So basically, like how important do you think doing research uh, in the days of an undergrad really is? Like, do you think that played a very important role in you being the kind of researcher you are today?
Yeah. I think actually doing undergraduate research is in some sense much more important than doing like coursework for a couple of reasons. One is it's really what, practitioners do. Like they don't take classes and they're not, solving problem sets. Research is much more open-ended and you often don't know like what the right way to go is immediately. And so, like when you're doing undergraduate research, of course, it's much more, guided by what the advisor is telling you. But even then, right, there's lots of places where things can wind around and, it's not totally clear how it will work out initially. And so I think it's important because it helps to, give you a sense also of what it would be like to be doing this, more full time. Because that's really where, of course, the coursework is important. You have to know the foundations. But it really is important to do, I think, some kind of research. I will also say, just from like a point of view of like applying to graduate schools or things like that, that is one of the things that, basically graduate admissions like look for, like, because that's what you're basically going to be doing in graduate school and beyond if you stay in like academia, which is research, not so much, coursework, but really research. And so, especially for me, I found that like, I would try to do well in my courses as an undergraduate, but it was really the research part that fascinated me. And that was, where I wanted to spend all my time and think about things. So, so I would say that it's actually very, very important to, do it. And also, for no other reason to see if you like it. If you don't like it, then, you should know very early on rather than, go to graduate school and discover, oh, I don't like this at all. So.
So that is basically a note everyone as an undergrad will now make. So basically, you are like quote unquote like one of the top string theorists in the world. When did you got to know about string theory in a non-technical sense?
When did I get to know about string theory in a non-technical sense? So I would say I kind of knew about it starting in high school, but I learned more about it, starting out as an undergraduate. I don't know. Initially, I actually wasn't that impressed with it and I wasn't that excited by it. I was more excited by things that were closer to experiment, just because of, where I'd been coming from research-wise and so on. It has a reputation for being abstract, and all the, more down-to-earth people I would talk to would say, oh, well, why are you, spending time thinking about this abstract thing? But after a while, I started reading more about it, not just in popular accounts. So like, I read some of that, and there were these exciting things happening with, like information connected with like, it's like the, counting the microstates of black holes. So this famous result of Strominger and Vafa. There was the ADS-CFT correspondence. So all these things, by the time I started getting interested in it, had already been kind of like established. And these were already kind of like pretty amazing results that, if something was going to be wrong, that, this did not sound like it. It sounded like it was doing a lot of correct things. And so, so for that reason, at some point I just said, well, this looks like it's, it's clearly, got a lot going for it. And so I want to think more about it. And so that's kind of how it developed. And again, I was kind of fortunate, like, as an undergraduate, there were lots of string theorists I could talk to, both, faculty or professors, postdocs and graduate students. And they were all pretty, encouraging and like willing to talk to me, even though I didn't really know anything. And so, the chance to really talk with them and find out like what was exciting to them also helped kind of spur me on to think more about the subject. So, so it kind of was like a gradual thing where I didn't know very much about it and I was skeptical at first, but then as I learned more, I realized, it seemed like it was really exciting. So, yeah.
Yeah, that is great. So like, when did you get your first technical understanding of string theory, and like, what did you make of it then?
Right. So, what I did, so I guess I had like a sort of miniature research project that I did with faculty mentor, Kurt Callum. it was more on the quantum field theory side than on the string theory side, but there were clear connections to things connected with, to topics connected with string theory. So he kind of phrased the problem to me as like, you can do this like quantum field theory calculation. And then he mentioned like, it's connected to these other things in string theory. So that was kind of my first exposure to it, really just on the quantum field theory side, like looking at that. Then basically, I basically at that point I was very excited about this. So I started taking quantum field theory classes as an undergraduate. And then I had the chance to take a string theory class with Polyakov in my senior year. And I mean, to be honest, like he didn't want to use a textbook. He just kind of like would, I mean, I'm not even sure he prepared notes in any kind of, traditional sense. He would just go to the blackboard and start talking. And, I didn't really know what was going on in the class. I mean, he was writing a lot of stuff and, it was very inspirational at some level because Polyakov is obviously one of the big giants of the field. But at the other time, I didn't know what was going on in the class. And so I kind of had to discover books for myself to kind of learn it at a technical level. And so basically, I asked like some of the graduate students even like, what do you recommend? And, one of them said, oh, you should use Polchinski's book. So I tried that and I didn't get very far in that. And so then I started looking online and I saw that there was a book being used by Clifford Johnson on D-branes. And this book, it had a much more intuitive flavor to it and it felt like he was speaking to me about like how to think about these things. And that was really the book that at a technical level was my first, I would say, real exposure to the subject because he went through, all the main topics pretty quickly, but in a way that, kind of made sense to me. And then I could go back and look at, things like Polchinski, which is at some level a more, detailed account of these things. But I would say it was really, Clifford Johnson's book that really helped me out quite a bit initially, like in my first kind of technical exposure to like how the whole subject fits together. I mean, I should also say that like I was talking a lot with like faculty about, these things, but, there's only so much they can do. So that was in, I guess, the fall. And then in the spring, there was another course offered by Steve Gubser, who, was one of the, let's say, co-discoverers of the main results or the main early results of ADS CFT. And his course was much more structured, and I was actually working with him on a research project at the same time. And so I got a lot out of that, and he really had a very clear way of presenting everything. And so I would say the combination of all that was kind of what kept me going and thinking about the technical side of it and getting more interested in that part. So
that is so inspirational. So you started doing great research in your undergrad, then you continued it in your grad school. And then finally, how did you feel when you wrote your first research paper?
So my first research paper, I guess, that was ever published was actually an experimental result related to like hyperpolarizing xenon 129. And it was one of these things where I had written like basically like a lab report. And I had handed over the main results of the lab report to the professor in the group. And then he basically spent the rest of the time turning it into a paper. And then I was kind of informed like, a little bit, a few months later, oh yes, this has been, submitted to a journal and it was accepted. So at that point, I was excited about it, but, my level of connection to the, final publication process was actually a little bit disconnected. It was more like, well, I had done the results and then the professor was kind of the one kind of finishing it out. That was true also for, I guess, my first paper in string theory too. Because in that one, I was working with a professor, but there was also a graduate student at Caltech who was very, very good. And so, again, I did like a lot of the computations and things like that. And I basically wrote a lab report about like, or a summary of what I had done. And then the graduate student at Caltech basically then went on to kind of finish it out and turn it into a paper. And I emailed him one time saying, is there anything I can do? And he said, oh yeah, we're finished with that and it's going to come out soon. So the first paper where I really like was involved at, every single stage in both, computing the results and then writing it up That was a paper I wrote with Steve Gubser, and it came out basically like all the stuff was in like kind of an undergraduate like thesis type report, or an undergraduate thesis that I'd written when I was an undergraduate, but it didn't get completely finished and finalized until graduate school. Basically, my first few months in graduate school, and for that one, really we were involved like at all stages, like writing it back and forth and so on. And so, again, I mean, Steve was playing, he was doing a lot of the, important work and making it, presentable as a research paper. But that was the kind of first one where, I was really involved at like every single stage of the process. I'll just say that then, like, my next paper didn't come out for a couple of years, and that was with Kamran Vafa. And for that one, it was, I basically had, he was advising me, but then basically said, I want to see, if you can do this, so it was much more challenging for me because I had to, then write the whole thing. And then he would basically say, no, this is no good. And then I would have to redo it. And then I had to keep redoing it because he kept telling me this needs to be improved. And so that was kind of the first really one where I was kind of like almost all on my own. But of course he was playing the, important role of like telling me what to think about and what to think about researching. So, yeah.
Yeah, that is like completely great. Currently, you told about all the papers in which you were like co-authors with someone. So basically, what was the first paper you wrote completely on your own as a single author? And like, what is the difference when you write a paper as a co-author and when you write it as a single author? So basically, what is the whole like the difference in the process as a whole?
Yeah. So I would say actually most of my papers are with co-authors. And so when was my first single author paper? It may not have been for a while. Trying to think. It may have actually been when I was already a professor or something, because I usually collaborate with people pretty intensively. So, I mean, for my own process of like doing research is more like kind of a back and forth process with the collaborators. And so, when you're doing that kind of thing, it becomes clear that there's a common set of things that you want to explore. And then it really depends on who's in the collaboration. Sometimes we'll each go off and do our own computation and then compare, how we all did the computation. And then sometimes we'll, be doing different computations and then seeing how they all fit together. And then we'll be checking each other's computations, but it won't be it won't be like one person, like everybody is doing the same thing. So it really depends on the particular project. So in those cases, right, there's a sense in which everybody has their own kind of responsibilities. In many cases, the role I often play in a lot of these research projects is I'm thinking about like what the general idea would be and, what kind of computations I want to do, but then also kind of like formulating it and writing it down, because that really helps to kind of crystallize what direction the thing is going to go. And that's more on the collaborative side. Now for like single author papers, at some level, it's much more challenging and kind of lonely because you've got to think of the problem yourself, and you've got to make sure that everything you do in the paper is correct, and nobody is kind of helping you out to check it and make sure that it's okay. So that puts a lot more responsibility on you to kind of make sure that everything is correct. So on the other hand, it's also, of course, much more exciting because then, like when you have a paper with multiple people, someone can always say, oh, yes, but what did this person actually do on the paper? And, there's always that question about, well, I can't really tell from the author list who did what. I mean, I will say that, once you know more about various writing styles and like styles of people's research, then you can usually tell like who did what, because you can say, oh, this person is an expert on this part and this person is expert on that part. And so you can kind of reconstruct, in many cases, what somebody did. Not always, though. I mean, in some cases, a person who's not an expert in something will, by purpose, want to work with an expert to just learn more about the subject. And so they will actually be the one driving the full project. So yeah, so in my case, I actually enjoy more like collaborating with people, and so I actually don't have that many single author papers. I think it's more like I'm always working with other people, talking to them, because I find I think more efficient and more productive, at least for me, to have a lot of things going. And it's kind of like the advantages of like parallel processing in computing. Like if you have lots of different things going at once, then there's a sense in which there's a chance for higher success, I think. Well, that's my own feeling, but there's obviously different perspectives on this.
Yeah. Yeah, that is great. Yes, yes, so, yeah. So currently, you're working on string theory, which, as many of us would know, is a possible theory of everything, and at the same time, it is one of the many quantum gravitational approaches that there are there. So how do you so how do you view the future of string theory and quantum gravity research as a whole?
Yeah, so I think it's actually pretty promising, just because the questions aren't going anywhere. So these are, there's clearly very deep questions in the subject. And so, at some level, even if there aren't that many people working in the subject, I mean, if you take the total number of string theorists in the world, it's probably on order of like, 1,000, 2,000, something like that. It's not like a huge number of people, but the kind of questions are very intellectually rich from a number of points of view, both in terms of connecting to our universe, in terms of quantum, how to combine things like quantum mechanics and gravity in one framework, but also in terms of kind of the other structures that appear. So structures connected with predicting new kinds of quantum field theories, new kinds of mathematics. All these things are kind of all part of the kind of string theory paradigm going forward. So what I would say in terms of like what I think is particularly promising, it's kind of developing kind of themes that have already existed, but I think that's that's only part of the story. I think one of the things that historically has been the case, especially in like a subject like string theory, is that you have people investigating things that are completely different than people would have thought of like 10 or 20 years ago. So I mean, just the history of the subject itself, right? It started off as kind of this funny model of strong interactions or something like it, and it's completely evolved since then. I mean, and it's gone through several mutations and iterations. And so the point is that this mathematical framework seems to be flexible enough to start accommodating many different types of formalisms and many different kinds of ideas. And the fact that it kind of continues to kind of grow and absorb these different areas of research, I think is actually very promising, and it suggests that, well, to me, it suggests that it's on the right path, but also that it has a very promising future. Now, that's from an intellectual standpoint. Of course, from a practical standpoint, like jobs and things like this, it's a bit it can be a rather different story. I mean, I think that's true of theoretical physics in general, and also just areas of science that aren't necessarily as tied to kind of practical industrial issues. So I mean, of course, there's going to be more emphasis in an economy and things like that on things that make money and things that have more direct impact on a day-to-day basis for people. But having said that, I mean, long-term investments and things that are of a more theoretical nature, these things have potential to kind of reshape the way we think about things in the world at large. And in many cases, applications that you may not have even thought about existing will turn out to be there. But you won't know about that until you kind of go look for it. So I think the fact that historically it's kind of had this process of kind of having ups and downs in terms of job markets, but also in terms of just like this overall intellectual growth in the subject that just kind of brings in more and more areas. I think it's very promising. So that's my own feeling on.
Yeah, yeah. And yes, that is quite a fascinating a take on this. So like you were talking about the practicality of string theory. Like how do you think we would get our first viable experiment test of any quantum gravitational approach which we have today? And like, would it be through cosmology?
Yeah. So I think cosmology is obviously a very natural place to look for these things because you're dealing with things that kind of bring together like the very microscopic and the very macroscopic, and that's precisely where you'd expect things like quantum gravity, which are also kind of intrinsically tied to these kinds of things showing up. So cosmology, I mean, I remember like hearing about like the announcement of, well, it turned out to be a false announcement from Bicep 2 about the gravitational waves that they had found. I mean, or the tensor mode fluctuations, that kind of thing. So the tensor mode fluctuations was an example of something where it was very exciting because it looked like it would be a direct access to kind of quantum gravitational phenomena. I mean, it turned out to apparently be a little bit more subtle to see anything like that. But yeah, cosmology for sure is like one place where you might hope to see kind of these things coming together. But I mean, I would say also that there's other ways in which it may not be like a direct signature, but more indirect signatures that are potential or another way that it may not be like a direct confirmation of anything to do with string theory, but it would be more like, strong supporting evidence that something is going in that direction. So a classic example of this is, LHC research for supersymmetry and things like that. So, they haven't seen supersymmetry, but also like string theory doesn't really say precisely where supersymmetric partners should start showing up. It seems to be a necessary feature of all kind of self-consistent string theory constructions that supersymmetry will show up at some energy scale. It's just not clear when. So seeing something like that would be kind of strong evidence that some of the ingredients necessary to make string theory make sense are really, manifested. So there's other things like that I also like to think about, which involve kind of the fact that string theory seems to predict new kinds of quantum field theories that don't appear to have like textbook definitions. And these are quantum field theories, and so they make observable predictions. Observable predictions you can see in various kinds of particle physics experiments. So this is another way in which kind of string theory might start making contact with experiment. I mean, yet another way is that these methods from string theory often involve taking kind of various like strongly coupled quantum systems of various kinds, and then rephrasing a lot of the strong coupling phenomena in terms of just purely geometric questions. And strong coupling phenomena are not just limited to questions in, say, particle physics, but other areas. So like other kinds of condensed matter systems. And so I wouldn't be surprised if, some kind of geometric construction would, from string theory, provide insight, theoretical insight into kind of even like tabletop experiments. So this has been a really big field involving like modifications of ADS-CFT correspondence to condensed matter phenomena, but just more broadly, using methods from geometry and string theory to understand kind of even like tabletop experiments. These are all kind of different ways in which you could imagine that kind of these techniques or these ideas would start to filter down into things that are can be probed in terms of an experiment. So, I mean, yes, cosmology is like obviously a very canonical place to be looking for it, but I think that there are other places that you can expect it to show up. I mean, I will also say if you view kind of mathematics itself as like an experimental field, then string theory has already made a number of like impressive predictions that mathematicians are kind of baffled by. And so it seems to always predict correct numbers in a lot of cases where, the mathematical techniques are kind of only being developed now. So this is another place. This is actually, I think, like one of the main places where string theory has been making predictions for a while now, and then they've been borne out by, it's obviously not like an experiment in nature, but it's still some kind of experiment because it's being verified by a mathematician in the form of like proving a result or something like that. But these are things that came from string theory and are then being predicted later on, or were predicted and then verified later on. So all of those are kind of ways in which, I'd say string theory makes contact with the broader world, in particular, like different kinds of experiments.
Yeah. So that is great. So you have worked on a particular part of string theory quite extensively, which is S theory. So, like, can you describe in uh, uh, like in just layman terms as to what F theory is?
Okay, so I don't know if I can do it in completely layman terms, but so in string theory, what you often do is you consider kind of the splitting and joining of strings, and it's controlled by it's controlled by a parameter, which is sometimes referred to as G sub string. And the strength of this thing controls the probability that an individual string will split into two pieces. Now, to actually do the computation, you have to assume that this parameter is very, very small, at least in traditional string theory calculations. So the point is that you have to assume it's small because otherwise you don't have any kind of good approximation. So you want to say it's a leading order, it's just one, and then there might be some small, tiny correction to it, which is the probability that the thing will actually split into two pieces. And this is kind of, the splitting is kind of the quantum effects of the string kind of moving around in space and interacting with other strings. So in F theory, the question is, how would you ever deal with the cases where this parameter, G sub string, is not a small number? Suppose it is order 1. So there's no sense in which you can kind of do an approximation. So there's like 1 plus basically another thing of order 1 and so on. So these are big corrections to these things, and you might ask, how could you ever do a correction or a calculation in this kind of regime of the system? And so what F theory does is it's a technique for kind of understanding what happens to string theory in that kind of limit where things are very strongly coupled. And the idea is to think of this parameter, G sub string, as really setting the shape or the size of a geometric object, like a two-torus. And because it's controlled by some geometry, it then becomes possible to say more about what kind of things are possible in the system. So for example, the very fact that you now replace it by a kind of geometry means that you can almost use things like the Einstein field equations for general relativity and things like that to understand what is going on with the strength of this coupling and how it moves around in space and time. So F theory at some level is like a way of taking these physical questions and then repackaging them in terms of better understood geometric questions that can be understood using methods from, say, Einstein's theory of general relativity, and also just from more abstract math. And so that at some very broad level is what F theory is attempting to address. Like what happens to strings when they interact, but they interact with like strong interactions with themselves.
So we have a question from the Instagram handle. Someone asks that one of the great places where scientists like usually meet are scientific conferences. So what was the experience that you had in your first ever scientific conference?
Oh, my first ever scientific conference. Well, so the first one I think I ever attended, it was kind of funny. I think it was like one of these things. It's called like a Texas Symposium in Cosmology or something, but it doesn't take place in Texas. It's I think like the first few of them took place in Texas or something. So it turned out, so it was in Chicago, and my dad he decided, okay, this was in high school. I'd been talking about physics or something like that. So all right, well, let's just see if he's, wants to do it. So, so he bought, he paid for my admission to go to this thing. And then he just said, okay, show up. And then he just left me there. And so it was a cosmology conference. But I remember one of the things that I did see is, so I got to see Roger Penrose give a talk there. And he had like a big stack of transparencies. Nobody wanted to talk to me because I was like a little kid in this, like they're all like grown-ups. But I stayed there, and I sat in the halls. I don't think I actually talked to Penrose, but I was really close to him. I could see him. But he gave a talk. That's basically all I remember from the conference. I mean, I think there were some other talks on like cosmology or something, but it was just basically me sitting there and kind of by myself, just looking at everybody else and seeing how they were interacting with one another. And I remember actually in between breaks, I was sitting, there, and like Penrose was a few aisles back behind me, and he was talking to somebody else about something, giving him like some advice on a calculation he was doing. So, so I remember that. So that was I think my first like experience at an actual like scientific conference for professionals. Now, I mean, the first one where the first one where I was really kind of more involved was actually a mental conference for NMR, nuclear magnetic resonance, and so there I was presenting a poster on the project that would eventually get turned into this paper. And so I remember I was at a poster session. I was just sitting there, as an undergraduate, just standing in front of my poster next to a bunch of other people with their posters. And that was much more, face-to-face and in person, because I was talking to people about what I had done, what I had computed, and so on, what I had measured and so on. And so, that was also a lot of, that was like the first really direct interaction. And so some of the people were very, friendly and nice. And one guy actually made a point of saying, "Oh, your thing is no good, and I'll tell you why in my talk tomorrow." so that was the other thing that happened at that one. Let's see. And then the first, I don't know. I mean, gradually what I learned is that, and then I started going to more like string theory based conferences. And in those, what I learned is that, the talks were kind of like the talks at the conferences were only kind of part of the story. And that at some level, the more important part of the conferences was really kind of the breaks in between the conference, in between the talks. And because then it was really that people would that was really the more. So anyway, so for that, it was really, the interactions in between the talks. And I think that's actually one of the things that kind of is missing a bit in, these like teleconferences that are taking place now, which is that, the kind of in between, just informal discussions. I think I've had a lot of papers start that way, or a lot of projects start that way. We're basically in between like talks. I'll be talking to like, either somebody I've known in the past or somebody I want to talk to. And we'll just start striking up a conversation on something. So that process kind of took a little bit longer for me to get comfortable with, because, when you're a very shy person and, you're not interacting with, you see all these, people you've heard about, and, you're not sure how to even approach them or talk to them. And, some of them seem friendly, but some of them, they don't seem so friendly. And so it's not totally clear. And so what I noticed in many cases is that, the graduate students would kind of clump together, and the postdocs would kind of clump together, and the professors would kind of clump together. But there were always a few people who would kind of like move around and mix a lot. And those were kind of, I tried to kind of emulate that a bit more, because I felt like that was potentially like a much better use of time for the conferences. So anyway, that was kind of a long answer, but those were my experiences with like conferences starting out.
Yes, that is wonderful. And actually, he followed this up with yet another question. And the question is that actually he is a senior in undergrad, and he is going to be presenting a paper next year in a conference in September. So basically, like he wants to know, like what should he be doing in the conference? Should he only focus on his presentation, or should he focus more on making connections?
Well, I would say actually both are probably very important. So when you're actually giving a talk, that's the other thing, right? If you give it like for talks, of course it's important to let people know, like, this is who I am, and this is what I'm working on, and this is how you kind of represent. I am like one of the people working in this area, and this is what I did. So they will remember that. But the other thing is that you have to make sure you do a good job on the talk, because there will always be a person who remembers if you gave a bad talk, and it could be like years past. Like, oh yes, I remember that guy. He gave a bad talk. So it's not. So you don't want that to happen, obviously. But often what happens in a lot of cases, right, is that the two are not kind of disconnected from one another. You give a talk, and then people want to ask you more questions about it after your talk, and that's the two things kind of go together in terms of making connections and learning more about what other people are doing. So, but it's also on the same time, right? It's not just you giving the presentation. It's also potentially asking questions of other people who are giving talks and making, finding out what interests you. So it should be more like an organic type thing where, you're interested in some area and you want to find out who are the other people in the area that are doing similar things. So that I view as kind of like the good part of like, going to a conference. I mean, when these conferences get to be too big, it gets hard to interact with people anyway. So that, if it's a reasonable size and you can still interact with people and get something meaningful out of it. Like if it's thousands upon thousands of people, like these giant meetings with lots of parallel sessions, it becomes very hard to, interact with everyone. And so then it becomes even more important to foster connections. So it really depends on the kind of conference it is. But I would say both are definitely important, and they aren't necessarily at odds with one another. They're kind of connected to each other. Yeah.
Yeah. Yeah. So actually, we have just like one more question, and this question is also from the Insta handle of the talk. So basically, so the questioner wants to ask that, like these days, loads and loads of particle physicists are joining the quantitative industry after doing PhD or a postdoc. Uh, uh, so basically, is quantitative finance also a kind of escape route from the academia for a particle physicist?
Yeah. Yeah, I would say yeah. So that's something that a lot of my friends who got PhDs either in particle physics, condensed matter physics, or just pure math. That's definitely a route that a lot of them have taken, either right after their PhD or after like a couple of years as a postdoc. So I mean the reality is that the number of academic jobs is pretty low. So there can be different things in play, right? One is the number of jobs is low. And if you're really excited about it, then, I think you should just keep trying to do it. But, at some level, reality will catch up eventually. And so, if you're on like your 5th postdoc or something, then it's not so great to be stuck in that kind of trajectory. And so, yeah, a lot of people I know go into quantitative finance, particularly aspects connected with like machine learning. That's become like a very important area inside of quant finance, and also things connected, just with using statistics in some way to kind of learn about building portfolios of some kind. Tech in general, like machine learning, again, is like one of these things that is being used in a lot of areas. And there's a number of physicists across different areas that are involved in machine learning because there's a very, there's some very interesting like physical ideas at play in like how, machine learning seems to work. And so kind of developing that both at an academic and, just from an industry point of view is something that has drawn a lot of attention for people going into transitioning from, say, academia into industry. So that's another kind of definite line through like tech, data science, things like that. Those are kind of canonical routes. I also know people who have become, science writers, and people who have decided that, well, they're not so interested in, the research side of things, but they still want to present some of this stuff to other people. So they start working in kind of like some level of just writing popular articles, or just developing like even like informal shows for explaining like what is going on to a broader audience, which because people are very fascinated by a lot of the kind of things going on in theoretical physics, but it can be very difficult for a practitioner to explain that in terms that are understandable to somebody who's not an expert. And so there is a role to be played by people who just want to focus on that part, make it more accessible to a broader audience. So that's another kind of natural trajectory, in addition to like quantitative finance and things like that. Let me see if there's anything else. I mean, there's obviously people who just decide to do something completely different, and that's you'll have that no matter what you do. But those are kind of like, I think, several like typical routes I've seen for a lot of people I know.
Yes, so I think that concludes the interview. Thank you so much once again, sir, for uh, uh, like a really inspiring and at the same time a very informative talk. And I think all of us at the CYWF team would like to infinitely thank you for this, and basically thank you so much for everyone for tuning in, and we will see you next time. Thank you.
All right. Well, thanks very much.